Good afternoon, everyone. I hope my slides are visible and my voice is audible to you all. So, I welcome you all to the sixth tutorial of this course, Introductory Organic Chemistry 2, which is conducted by NPTEL, whose course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputre from ISER Pune. I am Deepika, your PMRF teaching assistant. I am doing my PhD in chemistry at IIT Bombay. And today on 30th September, we are going to conduct the sixth tutorial for the course. Till now, in five of the tutorials, we have solved various tutorial questions related to the topics which are taught by Professor Harinath Chakrapani sir in his video lectures. So, in this week, the topics were related to various condensation reactions. Okay. In last week, we gave a brief introduction towards aldol condensation. Okay, so in this week also we are going to learn a few mechanisms and questions on the topic aldol condensation as well as some other related condensation reactions. Also, we will learn enolate equivalence and how they participate in various organic chemistry reactions. So, and the mechanisms that we are going to learn today are going to be very helpful in understanding how to approach mechanistic problems in organic chemistry. Okay, so let us start with the questions. Okay, so first question for today's tutorial: which ester will not give a good yield of the Claisen condensation product with sodium ethoxide in ethanol? So you are given five esters here and you are asked which one of these four will not give you a good yield. So before moving to the answer or how to solve it, let us revise the topic of Claisen condensation and how the mechanism goes. Okay, what happens in Claisen condensation? You have acidic protons, alpha 2 electron withdrawing groups. And what happened? Ethoxide or methoxide, whatever base is used for the condensation reaction, that base extracts an acidic proton alpha to the electron withdrawing group. So after the extraction, you get a carbon ion first, which is in conjugation with this carbonyl group. So in turn, by pushing the electron pair of the carbon ion towards the oxygen, which is definitely more electronegative, you get the intermediate enolate. Okay, so enolate is the main intermediate which is forming in Claisen condensation. And then we introduce the second substrate for the condensation reaction. This could be another molecule of ester or this could be a carbonyl compound. Okay, maybe ketone or aldehyde. This is not necessarily ester. Okay, the first molecule has to be ester and then the enolate generated undergoes attack at the second substrate which is having a carbonyl group. Okay, this enolate comes back to give you the CO double bond back and it attacks from this carbon. Always remember, in Claisen condensation reaction, you get the CC bond formation between the two substrates given. Okay, so then when the enolate attacks at this electrophilic center, you have to push the shared electron pair of carbon oxygen double bond towards a more electronegative oxygen. Okay, and since you have already formed the carbon-carbon bond, this intermediate product you are getting. Okay, this is actually written in the reverse way. This fragment is coming from the first substrate, isn't it? And this is the newly formed carbon-carbon bond. Okay, and after pushing the shared electron pairs towards oxygen, we are getting oxyanion here. So now, since the reaction conditions are basic, you cannot simply protonate this oxyanion, isn't it? So it has to get neutralized. How will it get neutralized? It will push its electron pairs back to regenerate the carbon-oxygen double bond, and it knocks out the ethoxide. Okay, or whatever leaving group is present. Okay, here it is ethoxide. OET is present, which is a good leaving group. So when the oxyanion pushes its electron pairs back, this ethoxide species will be knocked out. And then you get this product. Okay, this dicarbonyl, you can say beta keto ester, you observe. Okay, so this is the product for Claisen condensation. Now in the first step, you see that in Claisen condensation, the base is simply abstracting the acidic proton. Okay, more is the acidic proton here, more will be the rate of Claisen condensation. So you must note down that acidity of these two protons will depend on how much the carbon ion generated here will be stabilized. Like suppose in this carbon ion you see, okay, if this carbon ion is this negative charge is stabilized at this center, then the rate of the reaction will increase, okay, because we are getting a stable carbon ion here. But if you get a electron donating group attached here, you will simply have electron repulsion kind of situation in this step, isn't it? You have to pull the electron pair from this carbon ion center so that it is stabilized. We already have this ester center. Now we are left with this R group. If this R group is pulling the electron pair from this carbon ion center, then you are good to go. Okay, you will get a good Claisen condensation because in the first step you are getting a stabilized carbon ion. But if in place of R you have electron donating group, strongly electron donating group if you have, then you will have electron repulsion here. So this concept is going to help you in answering the first question. Okay, so which ester will not give a good yield of Claisen condensation product? If we look at all four substrates, in A, you have this ester, and to abstract proton, you have CH3 here. That means if we consider R adjacent to the CH2, you have only hydrogen here. Okay, just look at this one and relate this structure to all the options given. This will be H, CH2 and the ester group. And then in second one, you have adjacent to CH2, you have CH3. Okay, fair enough. Methyl is here and hydrogen is here. And then in third one, you have two methyls. Okay, two methyl groups are donating their electrons towards this carbon, from where we are going to abstract the proton for Claisen condensation. And in the fourth one, you have chlorine. Okay, so if you compare the acidity of these CH2 CH here, like the alpha proton to the ester group, if you compare the acidity, the least acidic will be this one, isn't it? Because you are getting electron donation from two methyl groups here. In first one, only hydrogen is going to affect. In second one methyl is donating. Okay, fine. But in third one, two methyls are donating its electron pairs, making this carbon highly electron rich. So, in Claisen first step, if you want to generate a carbon ion at this carbon, you will not get a good rate because you will have electron donated by these methyls and electron from the carbon ion repulsion. Okay, so that is the concept. The acidity of the proton will decide how good your Claisen condensation will be. Okay, so the answer is option C, because of because of the electron richness of this carbon center. Okay, so this is a brief explanation of the question. What I explained, you may note down that for Claisen condensation, you first need a stabilized inolate, which will be generated by extracting the alpha proton of the ester. Okay, so that is the description. I hope you understood the explanation for the first question. And after learning Claisen condensation, let us move to our next question. What will be the product of the following reaction? You are given a nitroalkane here, and we are reacting this nitroalkane with ketone and aldehyde in presence of same condensation reaction condition, which is base and solvent. Okay, base could be sodium methoxide, any base which will abstract the acidic proton, and then we will get a carbon ion or enolate equivalent, which will undergo nucleophilic addition to the second substrate. That is the basic concept. Okay, and you are given 4 options here. So you are asked, as a result of this reaction, we will get nitro alcohol or okay, these 2 options are same only, nitro alcohol or nitro alkene or amino alcohol. Okay, out of these 3 types of products, which product will you get? So for to know the product, let us go step by step how the mechanism goes. So what happens, this particular reaction that is given in the question, that is called Henry reaction. Okay, this is also a type of condensation reaction that is called Henry reaction. So in the first step of Henry reaction, the base will abstract the acidic proton, which is basically adjacent to the nitro group. As you all know, nitro group, cyano group, all these are highly electron withdrawing groups, isn't it? So these groups will stabilize the carbon ion formed after extracting the alpha proton. So after extracting the alpha proton, you get this carbon ion intermediate, which can also undergo conjugation with this NO double bond, giving rise to this enolate equivalent. Okay, and then in the second step, like all the condensation reaction mechanisms, this enolate equivalent will undergo nucleophilic addition at this electrophilic center. After that, you get the formation of carbon-carbon bond, like in a similar way, which we saw in Claisen condensation. Okay, nothing is changed, just this substituent is changed, but mechanism wise it is exactly the same. Okay, so after forming the carbon-carbon bond, since we are pushing the electron pairs towards the more electronegative oxygen, we have the oxyanion. Okay, here you do not have any leaving group attached at the alpha position of O minus. Okay, otherwise we would have knocked out the leaving group, but we cannot knock out the alkyl substituents. And also in the reaction conditions of Henry reaction, we mostly used solvents which can protonate the oxyanion. Okay, so in this mechanism, lastly what happens, the oxyanion will take up a proton from the solvent, leading to the formation of this nitro alcohol. Okay, and if you had any leaving group here, we would have obtained nitroketone. Okay, and for that you will have to use anhydrous condition. Okay, no proton source should be used in the reaction. But here, since we have proton source and also we do not have any leaving group, we will get this nitro alcohol as the final product. Thus, for the given reaction, you will get beta nitro alcohols. Okay. So this is the Henry reaction. It is a combination of a nitroalkane and an aldehyde or ketone in presence of base to form beta nitro alcohols. So I hope the mechanism was clear. Let us move to the next question. Again, this is related to condensation reactions and also one new concept at the last step you are going to learn. Okay, so let us go step by step. You are given this beta keto ester and then we are treating it with base followed by the treatment with bromoalkane to give you this beta keto ester product where now you have this alkyl chain attached to the alpha position of ester. Then again we are treating it with base and this benzyl bromide to get A. And then we are going to subject A to alkaline hydrolysis and also we are going to heat it in the next step. And lastly, after this condition, you get B as the product. So you are asked, what is the end product B? Out of these four options given, what is going to be the structure of B? Let us look at the mechanism that this question is following. Okay, that is going to clarify the end product. Okay, if we go step by step. So let us look at the mechanism. In the first step, we are given this beta keto ester. Okay, and when we add base to it, it will definitely abstract the most acidic proton. Which one is it? It is this one. Okay, ethoxide is the thermodynamic product giving base, the list that we studied in the last tutorial. So in presence of ethoxide, you will get the thermodynamic enolate. So the proton abstraction will take place from this particular carbon. Okay, then you get the enolate first, and that enolate will undergo attack at the second step with bromoalkane. So this carbon will attack at this carbon to knock out the bromide, and in turn you get the given product. Okay, so this product is given. You were just not given A and B. Okay, so this product is given. This is simple proton abstraction, carbon ion generation, and then enolate, and the enolate will come back to form CC bond by attacking the bromoalkane at this position. So fair enough, till now we are here, and in the next step we are again treating this product with ethoxide base. So similarly, it will again abstract the acidic proton which is present here, isn't it? Because this proton, if it is abstracted, the carbon ion is stabilized in both the ways. Okay, this proton is from a active methylene compound proton. Okay, so this proton, the proton present at this carbon center is now again extracted. So after abstraction of this proton, you get a carbon ion here, which will again form the enolate with this carbonyl group, and the enolate will come back the way we have studied the mechanism to attack at this benzyl bromide. Okay, so this center is attacking at this center, so carbon-carbon bond will form between these two. And while writing the mechanisms, note down that you do not miss out any carbon. Okay, in the product you again count the number of carbons, because sometimes what happens when we attack at the bromoalkane with the carbon ion, we miss out carbon number sometimes. Okay, so when we are forming carbon-carbon bond between this carbon and this carbon, we have CH2PH attached at this particular alpha carbon of the ester group, and thus you get this product as A. Okay, it is the beta ketoester product where now you have alkyl change attached at the alpha position. Now in the last step, the beta ketoester, the new beta ketoester product which we got is now undergoing alkaline hydrolysis. So in presence of aqueous base, first what will happen? This ester group will undergo hydrolysis, and that will give you beta keto acid. And again, we are not stopping the reaction at that stage. In the next stage, we are treating it with acid and heating the reaction medium. Okay, so what happens in this particular step, which is not very common in the condensation reactions that we have gone through till now? Okay, this first step you all must have come across already. This is alkaline hydrolysis of ester, so you will get COOH here. But what is happening in the second step? So that step is basically decarboxylation of beta keto acids. Okay, so when you treat a beta keto acid in the given reaction condition, the compound undergoes decarboxylation. It eliminates a carbon dioxide molecule from the system, leading to the formation of either a carboxylic acid or a ketone, depending upon the reaction substrate. Okay, so for us in the question we have a beta keto acid now after this first step. Okay, so when we treat this beta keto acid in the heating condition, it first will eliminate the carbon dioxide molecule, leading to the formation of an enol first. Okay, but you must remember all acids cannot undergo decarboxylation in the given reaction condition. Okay, you just cannot treat all the acids with acidic medium and heat the system. You must have a beta keto acid to get a decarboxylation reaction in this condition. Okay, so in this way you can eliminate the carbon dioxide. This particular carbon dioxide molecule which you see by arrow pushing is leaving the system as gas. Okay, this oxygen is taking up this proton. This bond is breaking and coming towards this side, forming CO double bond, and it is eliminating. And this carbon-carbon bond is also breaking to give you carbon-carbon double bond here. Thus, this beta keto acid is first forming an enol which undergoes tautomerization to give you a ketone. Okay, so in this case, you will have decarboxylation from this ester after converting it to acid, and you have only the ketone group left here. Okay, so the product finally undergoes decarboxylation to give you this particular ketone as the final product. You can note down this reaction, which is decarboxylation of beta keto acids, and this slide is showing how a diacid and a beta keto acid is undergoing decarboxylation under the given conditions. Okay, you may note down. So thus the final product given is, which one is it? Option 4. Not option 4, is it? This is option 2. Okay, option 2 is the final product which you are getting after decarboxylation of the acid, beta keto acid. So this last step I know was a little uncommon for you all. I hope you understood, and with this let us move to the next question of this session. Okay. So in the next question, the major product formed in the following reaction is, you are given this diester compound and we are treating it with base sodium ethoxide in presence of benzene solvent in 80 degrees Celsius. Okay. So you are given four products and two of which are again beta ketoesters and the other two are not. So you have to figure out which product you are going to get when you treat this diester compound. Okay. So let us go step by step how this diester compound undergoes condensation reaction in presence of base. So till now, if you have understood the basic concept, what happens first? The base will abstract the acidic proton from the alpha position to ester. Okay, since this is a symmetric molecule, it will abstract the proton from either here or here. Okay, so like this, the base will abstract the proton, giving you the carbon ion at this center. If you do the other way, like abstract the proton from here, that is also going to be the same only. Okay, because this is a symmetric molecule. So after generation of the carbon ion, this carbon ion will undergo nucleophilic attack at the neighboring carbonyl compound present. Here it is the second ester functionality. So it will undergo intramolecular attack, giving you this oxyanion. Now you have a leaving group present alpha to the oxyanion. So the oxygen negative charge will come back, leading to the knocking out of ethoxide. Okay, so after knocking out the ethoxide, you will get this beta ketoester. Again, you are left with another acidic proton here. Okay, so when you have active methylene compounds, you have two acidic protons in between, isn't it? This is the keto group which is withdrawing electrons from this center, and this is the ester group which is withdrawing electrons from this center. So you are left with another proton, and the reaction will not stop at this step. So what happens? It can again abstract a proton from this center, leading to the formation of the second enolate. Okay, but you do not have a third substrate to undergo reaction. So when you work up the reaction medium, this oxyanion or this enolate will get protonate to give you the final result which after the workup, which will be this beta ketoester product. Okay, so after the intramolecular reaction of this diester compound, you will get this beta ketoester as the final product. So which one is this one? It is the option 3. Okay, you will get the option 3 as the final product for the reaction. So fair enough. After this, let us move to the next question, which is going to be a little long. The correct sequence of reactions involved in the following transformation is cyclohexanone you are given, and we are treating only this molecule in presence of sodium ethoxide base. So whatever condensation reaction it is going to undergo are going to be self condensation reactions. Okay, it is this molecule is undergoing condensation reaction with itself only. Okay, only one substrate we are taking in the reaction. So if we want this product to form, what are the reactions that we need to involve in the mechanism? So to solve this question, you have to first break up this molecule into fragments, and you have to identify what are the reactions that will lead you to the formation of those small fragments which we are going to combine to generate this product. Okay, let us start with option 1, aldol condensation, Michael addition and aldol reaction. So what will happen if this molecule will undergo aldol condensation with itself? First, it will abstract a proton, the acidic proton from this, and then it will undergo reaction to itself like the second molecule of cyclohexanone. Okay, imagine a second molecule of cyclohexanone here, and this particular center will attack at the carbonyl carbon of that second cyclohexanone molecule. And after this completion of this aldol condensation, you are going to get a product which is going to be this one. Just look at this intermediate product which we are going to come a little later. First aldol condensation is going to give you this product. How is it? Let us just quickly recap the aldol condensation. We have already learned it in the last tutorial. The base will abstract the acidic proton from here, leading to the formation of enolate, which will come back here and undergo CC bond formation to attack at this acceptor, leading to the formation of this oxyanion. And this oxyanion can take up a proton to give you this beta hydroxyketone, but in condensation you lose a water molecule from this center, and you will get a compound like this from self aldol condensation of cyclohexanone. Okay, so we were considering option 1, and from aldol condensation we have obtained this product. Now what we are doing, we are now introducing the second type of condensation reaction, which is Michael addition. How it happens? Not really condensation, but mechanism wise it is quite similar to aldol reaction. Okay, so what happens in Michael addition, you again have acidic protons. So deprotonation first happens to give you enolate from the carbonyl compound, and that enolate will undergo 1,4 addition to this kind of substrate, which are basically you can call alkyl vinyl ketone. Okay, in one side you have alkyl, in one side you have vinyl, so you can say that the enolate undergoes addition to this alkyl vinyl ketone. And after the addition, you get a carbon-carbon bond formation between these two centers, and in turn you get a carbon ion here. Okay, which can again undergo enolate formation with this CO bond, but in the last step this carbon ion will take up a proton from water in the system or moisture in the system to give you this diketone compound as a result of Michael addition. Okay, the first and second step are similar to the aldol condensation. So till now we got this product from aldol condensation. Now this molecule is going to undergo Michael addition with the third molecule of cyclohexanone. How is it going to happen? The base will abstract the alpha proton to give you the enolate, and this enolate is going to undergo Michael addition like we said. Like this center, if you treat, this is an alkyl vinyl ketone, isn't it? So this enolate is again going to undergo 1,4 addition to give you carbon-carbon bond formation between this center and this center. Okay, and as a result of this Michael addition, like we saw, we were getting 1,5 dicarbonyl compound. 1, 2, 3, 4, 5. This 1,4 dicarbonyl compound. So similarly, in this one, you are going to get carbon-carbon bond formation between this and this carbon to get this 1,5 dicarbonyl compound. Now, in the last step, what was our desired product? It was this one. So we have now arrived at this stage only. So to go from here to here, we are one step ahead. What is it? It is aldol reaction, simply aldol reaction, not condensation, because we are not going to remove any water molecule at the final step. So let us carry out the aldol reaction, which is going to give us the desired product. For that, when you treat this compound with base, now proton from here will be abstracted. Okay. Proton from here will be abstracted. Okay, because this is the more acidic proton containing one. Okay. So after the abstraction of proton, you get a carbon ion first, which is stabilized to give you the enolate, and then this enolate will come back to attack at this carbonyl group. You can also think of taking a proton from this side also, but that is also going to give you the same product. Okay, you can either take a proton from here and then attack the enolate at this carbonyl, or you can also take up the proton from here and attack at this carbonyl. Both ways you are going to get the same product. Okay, so in the final step, like you see, the enolate is going to attack at the other carbonyl moiety of the substrate, and finally you are going to get this hydroxyl group by protonating the oxygen ion formed in this step. Thus, you are going to get this tetracyclic keto alcohol as a product. Okay, beta hydroxy ketone you are going to get in the final step. I hope this was clear. It was a long question which involved not only one, not only two, but three types of reactions. This question involved. Okay, what are those? Aldol condensation, Michael addition, and lastly aldol reaction. So out of all the options given, what we saw, first we need to do aldol condensation to get this particular intermediate, and then we have to carry out Michael addition with this intermediate, and lastly aldol reaction from aldol reaction on this 1,5 dicarbonyl compound give you this tetracyclic molecule. Okay, so after solving this conceptual question, let us move to the next question of this session. I hope this was clear. So in this next question, we are treating this aldehyde with two equivalents of this bromoester, okay, alpha bromoester. We are treating with this aldehyde in presence of zinc in THF solvent. And this question is from actually a research paper. We will just look at the mechanism and you will be easily able to tell what product we are going to get in this reaction. Okay, so this reaction we have also discussed in the second last tutorial, that is the fourth tutorial. We have discussed this reaction, which was the Reformatsky reaction. Okay, let us look at the mechanism. What happened in Reformatsky reaction? It is an organic reaction which condense aldehydes or ketones with alpha haloesters in presence of metallic zinc. Okay, and the final product you get is beta hydroxy esters. So, like the definition of Reformatsky reaction, here also we have aldehyde with alpha bromoesters in presence of metallic zinc. So, if we talk about the simple mechanism, what happens? First, the metallic zinc reacts with the bromoester to give you this zinc intermediate, which is an organo-zinc compound, and this organo-zinc compound, which is formed from the reaction of zinc and bromoester, undergoes nucleophilic addition to the aldehyde or ketone given, and in that step you get this intermediate. And finally, in the workup stage, when you work it up with water or maybe acid, in that step this organo-zinc intermediate breaks up to give you beta hydroxy esters as the final products. Okay, so that is the simple mechanism of Reformatsky reaction. And if you want to look at simply like breaking the stages further, what happens first? The zinc undergoes oxidative addition to the bromoester to get this organo-zinc reagent. So this is the organo-zinc reagent which forms, and that organo-zinc reagent forms organo-zinc enolate in the next step. Okay, this is the enolate which is forming now, and that enolate will undergo nucleophilic addition to the electrophilic center of the carbonyl compound in the reaction. So this is the main transition state. You can imagine this organozinc enolate will come back to give you CO bond back, and this CC double bond will undergo attack at this electrophilic center. And now, since you get an oxyanion here, the counter cation will be the zinc bromide. Okay, and that counter cation will leave when you do acidic workup of the reaction, where the oxyanion will take up a proton from the system to give you beta hydroxy esters. Okay, so this is the Reformatsky reaction mechanism, which was published in a research article in Tetrahedron in 2004. So you can go through this research article if you want more information about this particular reaction, which is involving organo-zinc enolate and undergoing nucleophilic addition to the carbonyl compound. So let us go back to the reaction given in the question. Here, what will happen first? The organo-zinc intermediate will form here. Like here you can get ZnBr first, and that will give you the enolate formation. And that enolate will come back in this position, and here the carbon-carbon double bond of enolate will lie, which will undergo addition at this electrophilic center, leading to the pushing of electron pair towards this oxygen to give you oxyanion. So now you have carbon-carbon bond formation between these two carbon atoms. Okay, and what will be the counter cation of the oxyanion? That will be zinc bromide. Okay, so the ultimate product you get is the beta hydroxy ester. That is, overall result of the reaction, if you see, this carbonyl group is reduced into a hydroxyl group, isn't it? You get a carbon-carbon bond formation between these two centers and you get a hydroxyl group here. So if we talk about the product here, you will get carbon-carbon bond formation between two centers and here you will have a hydroxyl group line. Thus, the product that you are going to get in this particular reaction is going to be this beta hydroxy ester. Okay, so this is the interesting mechanism of Reformatsky reaction, and as the result, and you must note down that the mechanism is again quite similar to the other condensation reactions or addition reactions that we have studied today. First, the generation of enolate happens, and that enolate undergoes nucleophilic attack to the second partner in the reaction. So, the similar strategy is going to be used in the Reformatsky reaction, and you get this beta hydroxy ester as the final product. Let us move to the next example of the similar reaction, Reformatsky reaction. Okay, we will come to that a little later. In the next question, what are we doing? We are treating the cyclohexanone with this silyl enol ether. Okay, this is a silyl enol ether. Okay, and what will happen if we treat this cyclohexanone moiety with silyl enol ether in presence of, in the first step, this compound? You do not get scared looking at this compound. This is just a boron containing Lewis acid. Okay, so about the basic reactivity of the reaction, if we talk about, we are simply treating a ketone with silyl enol ether in presence of Lewis acid. So what reaction requires this condition that we have studied in the video lecture? It is Mukayama aldol reaction. Okay, and the second step is just workup stage or hydrolysis. So mainly focus on the first step. So let us look at the reaction mechanism that this reaction is going to follow. Okay, this is basically the Mukayama aldol reaction. So what happens first? The carbonyl compounds reacts with the Lewis acid given in the reaction medium, and this oxygen, which is electron rich, is going to donate its lone pair of electrons to the Lewis acid to give you this intermediate compound where the oxygen is going to be coordinated to the Lewis acid. Okay, so this Lewis acid is basically activating this carbonyl group for electrophilic addition reaction, because the shared already this carbon center is electron deficient because of the electron pull by the oxygen atom, isn't it? But now again the electron pairs of oxygen are going to be pulled by the Lewis acid, so this center is now becoming more electron deficient, even more electron deficient. Okay, so after this activation step, what happens? The silyl enol ether reacts with, undergoes nucleophilic addition to this activated carbonyl group. Okay, like if you see in the first step, we knocked out the chloride anion, and this chloride anion is going to attack at this silicon atom of silyl enol ether. And the driving force of this attack, if you ask, you always remember silicon fluoride and silicon chloride. These bonds are highly stable and strong bonds. Okay, so whenever you have chlorine or fluorine in the reaction medium, those will always attack at the silicon atom present in the system. So the chloride which got knocked out will now attack at the silicon atom of the ether, and this oxygen silicon bond will break to give you the carbon oxygen double bond formation here. And now this carbon carbon double bond of this enolate will attack at this activated carbonyl carbon. Thus you are going to attack uh, going to eliminate this trimethyl chloride as the byproduct of the reaction. And after the formation of carbon carbon bond between this green CH2 carbon and this blue carbonyl carbon, you will end up getting this kind of intermediate. Okay, the Lewis acid fragment is going to coordinate with both the oxygen atoms of this intermediate product, which is removed in the workup step, which is usually done in presence of acid. Okay, in Mukayama aldol reactions, acidic workup is done to remove this Lewis acid fragment, which is coordinating with both the oxygen, and this O minus oxyanion, which could be generated by the enol attack at the electrophilic center, that oxyanion is going to take up a proton in the workup step to give you this beta hydroxy ketones. Okay, so this is the mechanism that Mukayama aldol reactions follow. So, and remember, the Lewis acid is not necessarily titanium chloride all the time. It can be any Lewis acid, and organic chemists have been using boron Lewis acids or indium chloride Lewis acids. Various Lewis acids have been used in these Mukayama aldol reactions. So, this kind of strategy or mechanism is followed in all those Mukayama aldol reactions. Okay, so in the reaction, in the given reaction, if we look at here also, this boron containing Lewis acid is present. So what will happen? This boron in the first step will get coordinated with this carbonyl oxygen, which in turn is going to activate this carbonyl group. And also this silyl enol ether is going to attack at this activated carbonyl in the second step, and like we saw in this final step, in this reaction also you are going to get the formation of beta hydroxy ketones as the final product. Okay, so in the mechanism reaction you saw that chloride was breaking the oxygen silicon bond. In this particular Lewis acid, this fluoride ligands present are going to attack at the silicon to break this oxygen silicon bonds. And mostly this chloride or fluorides are used to break this oxygen silicon bond in silyl enol ethers. So in the product also you will get the beta hydroxy ketone as the final product, where the carbon carbon bond will be present between these two centers, and you will have OH at this position. No, not OH, CO double bond will be present here, and OH at this position, which will form due to attack. Okay, between these two centers you are going to form carbon carbon bond. So this is the product that you are going to get. If you want to write down the mechanism, you can note down the product and you can try out at home. If you face any difficulty in breaking the mechanism of this particular reaction, how we achieve this product, you can tell me in the next tutorial, and we are going to solve together the mechanism of this particular Mukayama aldol reaction. You just have to simply follow this mechanism and you will be easily able to get this beta hydroxyketone formation in the reaction. Okay, so I hope this was clear, the mechanism was clear. With this, let us move to the next question here. Okay, so here what is happening, we are taking an ester and treating it with 1.5 to 3 equivalent of silyl enol ether, again in presence of indium iodide catalyst. Okay, and this is additive. This one is additive, this is not participating in the reaction mechanism. Actually, in case of some Lewis acids, some additive compounds are added to increase the activity of the Lewis acid. Okay, so in this reaction, indium iodide is the particular Lewis acid which is acting as the coordinating partner of this carbonyl group of this ester partner for Mukayama aldol reaction. Okay, so we have already looked at the mechanism, and understanding the mechanism, you can start solving this question. What will happen in the first step? The Lewis acid which is given here is going to coordinate with this oxygen atom, which is going to increase the activity and electrophilicity of this carbon center. Okay, so now this silyl enol ether can attack at this activated carbon to give you carbon-carbon bond formation between this carbon and this carbon. Okay, you will get a carbon-carbon bond formation between these two carbon atoms, leading to the formation of oxyanion at this center, which is going to be protonated at the workup stage. Okay, so in the final step, okay, in this reaction what happens, since you have a good leaving group here, elimination of methoxide will be preferred rather than the protonation of oxyanion. Okay, because we are not keeping any proton source here, we are using DCM solvent, and also you have a leaving group which is a good leaving group attached to the carbonyl carbon. So in the final product you get elimination of this methoxide to neutralize the oxyanion formed. Okay, so you will get the formation of this product in the final step. Okay, so this reaction is also going to follow the same mechanism. Okay, so with this we have learned the various types of aldol reactions and condensation reactions, and also we talked about enol equivalents taking part in various related aldol reactions. For example, we talked about Reformatsky reaction or Mukayama-Aldol condensation. Not only that, we also talked about in today's tutorial Henry's reaction, Claisen condensation, and also Michael addition. Okay, all these mechanisms are actually interrelated, and the basic concept of the reaction, if you look at, is going to be the formation of enolate first, which will undergo nucleophilic addition to the second partner given in the reaction, and it could be self condensation or self reaction, and or also it could be cross if you are given two types of substrates. We also looked at types of intramolecular condensation or intramolecular addition types as well in the examples. Okay, let us quickly go through the questions that we solved today. So we started with this reaction, which ester will not give a good yield of the Claisen condensation product with sodium ethoxide in ethanol. So to solve this question, we went through the Claisen condensation reaction mechanism, and we saw that to get a good Claisen condensation reaction, you need strongly acidic protons alpha to the ester. Okay, so we saw that out of the four options given, option C was the one which was not containing enough acidic proton alpha to the ester group. Okay, and that is why we chose option C as the answer, which will not give a good yield of the Claisen condensation product. In the next question, we looked at the mechanism of Henry reaction, which is basically a addition reaction between nitroalkane and ketone or aldehyde, which give you nitroalcohols as the final product, and it was again following the similar mechanism as aldol and Claisen condensation. Okay, just because it is containing a nitro group particularly, that is why this reaction is called Henry reaction. Okay, the nitro group is making it distinctive. Okay, but the mechanism is exactly similar. Again, in the third question, we worked out this particular reaction series, and we figured out which of these four options given was the compound B. All the mechanisms were familiar to you except for the last step of this reaction, which was a decarboxylation reaction. And when we looked at the mechanism, after getting a beta keto acid to at this step, when we treated that beta keto acid with heat and acid, we got the formation of a ketone via decarboxylation. Okay, and also we talked about the mechanism which is followed by decarboxylation reaction, and we chose this product to be the final end product of this reaction. Okay, so after that we again treated this diester compound in presence of thermodynamic base, and we saw that this particular beta keto ester was getting generated via intramolecular condensation reaction. Okay, and the mechanism followed in this reaction is exactly similar to whatever condensation or addition reactions we have studied. Okay, so this is the product that we got at the final step. Then we move to this long sequence of reactions, and you had to identify what are the reactions that are getting involved in this reaction series. When we broke the reaction into various fragments, we came across aldol condensation reaction and also Michael addition, where we saw addition of enolate to to an alkyl vinyl ketone. And at the last step, we saw that Michael addition product that is observed is a 1,5-diketone compound, dicarbonyl compound. Okay, so similarly in the reaction, we first involved a Claisen condensation reaction to get this alkyl vinyl ketone, and this alkyl vinyl ketone underwent Michael addition with the enolate formed from the substrate given, and we got this 1,5-dicarbonyl compound. In the next step, this 1,5-dicarbonyl compound we treated with base, and we saw that it underwent intramolecular aldol reaction to give you this beta hydroxy ketone as the product. Okay, so after that question, we studied the mechanism of Reformatsky reaction, how zinc organometallic compound acts as an intermediate which rearranges itself to an enolate equivalent, which is a zinc bromo zinc bromoinolate, and how it underwent addition reaction we observed, and the end product obtained was similar to aldol reaction, which is a beta hydroxy ester. Okay, this was the reaction mechanism we observed, and that is the product. This beta hydroxy ester was the product that we got at the end. Next, we move to Mukayama aldol reaction, where we saw how this silyl enol ether underwent addition reaction to activated carbonyl compound. And the activation, how did we do? We did it with Lewis acids. Okay, we also talked about various Lewis acids which could undergo this activation process, and in the second step this silyl enol ether underwent addition reaction to the ketone. And this is the example mechanism that we observed in case of titanium chloride as Lewis acid. And the last step of Mukayama aldol reaction, in the last step the oxyanion took up a proton to give you the beta hydroxy ketone, a product which is similar to aldol reaction or Reformatsky reaction as well. And thus we observe that the final product for this particular reaction, where boron Lewis acid was used, we got this beta hydroxy ketone. And another example of the Mukayama aldol reaction we discussed, where we got this particular product as the final product. So with this we have come to the end of this tutorial, where we discussed various types of aldol reactions and also enol equivalents and how they participate in the reaction mechanism. So thank you everyone for joining. You may ask any queries if you have.